In the previous section, we created and configured a DMA FIFO. By the end of this module, you will be able to write to and read from a DMA FIFO. Okay, let's talk about how to use a DMA FIFO on your FPGA VI first. Okay, so now that we've created one in our project, what you can do is you can simply drag that DMA item from your Project Explorer onto your block diagram of your FPGA VI. Okay, so in this case, we've created a DMA FIFO that goes from the target to the host. So when we dragged it onto our block diagram, it automatically knew that we were going to try to write to it on the FPGA side. So on the left-hand side there, you see our write method for the target to host DMA FIFO. So if we take a look at that left one, notice we can write a new element into it. So there's a terminal for that. You can wire a timeout, and also you can see whether this timed out or not. Okay. Let's say we had a DMA FIFO and it was going in the opposite direction. So it was going and transferring buffer data from the host to the target. Well, if I put this DMA node on our FPGA VI, in this case, it would show up as a read. Notice on the read, there's an element terminal, and you can use that to read the next element that's available in the DMA FIFO. Again, there's also a timed out and a timeout terminal as well. You can use the timed out terminal to determine the status of the FIFO. So you can use these timed out terminals to determine whether there was an overflow or underflow condition. Okay, now that we've talked about using the DMA FIFO on our FPGA VI, let's talk about using the DMA FIFO on our host VI. So on our host VI, again, we're going to start off by opening a reference to the FPGA, like you see on that screenshot. And then the next thing you're going to do is add an invoke method function. And you're going to grab that from your FPGA interface palette. So once you've done that, you can select the method, and then what you want to do is navigate to the name of your DMA FIFO. In this case, we've named it target to host DMA, and then we're going to go to read, because in this case, because it's going from the target to the host, we're reading on the host side. So notice here on the left-hand side, if you had a DMA FIFO that was going from the target to the host, on the host VI, you would have a DMA read. So notice that on the DMA read, you can specify the number of elements you want to read at a time, and there's also a timeout, and data, that's where your data is going to come out. And you can also take a look at how many elements are remaining in that FIFO. On the right-hand side, we take a look at the other direction. So if you're creating a DMA FIFO to transfer buffer data from the host to the target, then on your host VI, you would be writing to that DMA FIFO. And on the right-hand side, we see that we can write data to it. Again, there's a timed out terminal, and you can find out how many empty elements are remaining in that FIFO. So now let's put these functions together and see how this might work in an application. So at the top, we have an FPGA VI block diagram, and at the bottom, we have a host VI block diagram. Let's take a look at the FPGA first. So on the top loop, we see on the FPGA that we're going at a specified loop rate, and we are just reading from an FPGA I/O node, and we're taking that data and putting it into our DMA FIFO. So in this case, we've created a DMA FIFO that goes from the target to the host. Okay, so let's now take a look at our host VI. Okay, so on our host computer, we have our host VI, and the block diagram on the bottom shows that. So the first thing we're doing in our host VI is we have a DMA read, and what we're doing is we're not reading any elements right now. So notice that number of elements is 0. We're also not doing anything with a timeout, so we're not going to wait for anything. We're just going to see instantly how many elements are remaining in that FIFO. So notice that we have elements remaining coming out, and then we're comparing that with a greater than with a fixed size. So essentially, we're waiting until we have enough elements in the FIFO that is 10 or greater. Okay, so in this case, we're looking for a fixed size of 10, and anytime there's 10 or more elements in that DMA FIFO, we're going to go to the case structure where it's true, and we're going to notice that we're going to read 10 elements. Okay, and notice that the timeout is also 0 here because we know that we just checked, and we know there's at least 10 elements in the FIFO, so we can go ahead and read 10 elements, and then the data coming out, that's going to be an array that contains 10 elements from my FIFO. So this is a nice method of being able to read a fixed number of elements, and it'll also be pretty efficient on your CPU as well. So if you take a look at the comment there on the bottom, there's something that says false case contains wait function that sets the polling rate. So in the false case of that case structure, so for example, if that first DMA read told that case structure that, oh, there's not 10 elements in the FIFO available yet. In that case, we can have a wait function in the false case that's telling the CPU to wait a little bit and set how often we want this loop to poll and check how many elements are left in the DMA FIFO. Okay, by having that wait function in there, we make sure that this while loop is not executing as fast as it possibly can and using up all the CPU. Okay. One other thing I wanted to point out real quick is the significance of having a 0 wired to the timeout. So on some RT targets, such as CRIO, if you have a timeout wired to a read, and you're checking for a certain amount of elements, so imagine we have a blank VI and we have a while loop on that host VI and it's running on a CRIO. And in that while loop, there is a DMA read and we have number of elements that it's trying to read. Let's say it's waiting for 100 elements. And the timeout was set to something other than 0, so maybe it's set to like 10 milliseconds or something like that. Okay? So let's say there's nothing in the DMA FIFO. Well, if that DMA read node is executed, it's going to sit there and it's going to use CPU resources to constantly check until the timeout expires how many elements are in that FIFO until it reaches 100. So what typically happens is the CPU, in this case, will go all the way to 100%. And we know, if you're familiar with real-time programming, you do not want your CPU to go all the way to 100%. Because at that point, we know we're fighting for resources and something in your program is not happening. So I just wanted to talk about that sidebar really quickly, just to show you the significance of having a 0 timeout, especially if you're running this host VI on CRIO. So in this case, if you look back at the host VI that's pictured on this particular slide, this is a good best practice. And remember, in the false case, you'd want a wait function that determines the polling rate. Now you can write to and read from a DMA FIFO. Next, we will handle DMA FIFO underflow and overflow conditions.